to find the inverse, you lay out the equation, and then you swap x and y, and then you solve for y, and you get the inverse. With exponents, you can't do that directly. Okay, so what we have to do is define an inverse. So if we go back to the original definition, of a function, we take a value in the domain of the function, and that function then maps it to a value in the range. And since we're talking about exponentials, we'll set up a function f of x equals a to the x. What we want to do is find an inverse to that. So it's the inverse that maps a to the x back to x. So if I know, for instance, if my function is 10 to the x, if I take a 2, then I get in the range, I get 100. And so what I want to do is have a function that when I give it 100, it gives me 2 back. All right. So we do this by defining the logarithm. So there's no real nice algebraic elementary function that will undo this exponent. So we define one, and we'll call that the logarithm. And if we have this expression here, this y equals a to the x, that's going to be exactly the same expression then as x equals log the base a of y. So the x and y correspond in both of these. So the x that's here, right up there, is the same x that you get out. So when you take the logarithm of a number, what you get is the exponent that it would take to apply to that base to get to that number. All right, so let me simplify that, take out the f's. And so we're going to call these two equivalent equations. The only difference between these two equations is the notation. The meaning is exactly the same. Okay, so we're going to look at the consequences of this notation and come up with some a set of rules that should be very practical for us to deal with logarithms. Okay, so we'll start out. 10 squared equals 100. That's the same as log base 10 of 100 equals 2. Okay, just making that kind of substitution of where the numbers are. And so you should get really good at this, is being able to go from one to the other and also thinking of these numbers in that context. So when we take log base 10 of 100, we're really asking what exponent do we apply to 10 to get to 100? All right, so that's the meaning of that. So now we've defined this thing e, and so e comes into logarithms as well, and so e to the x equals 2, and the log base e of 2 equals x. All right, now we're going to have a simplified notation for both log base 10 and the log base e, so we'll get to that. But let's look at doing a few more of these conversions. So you try, okay, make the equivalent expression to, or equation to this, okay? Write that as a logarithm. Now here, the thing that always kind of bails me out about how to do this, if I haven't used it in a while, is knowing what the things are called. Okay, so back when we were talking about exponents, remember we have this kind of a to the x. I guess this is not really writing, but probably well enough for this purpose. We call a here the base. Okay, we have x is the exponent, a is the base. And it's the same thing with logarithms, that when we talk about which logarithm it is, that's the base. And so whatever goes down here as a little subscript of the log is the number that's the base in the exponential. And so once you have that, then everything kind of falls in place. All right, so what does this one translate into from a logarithmic standpoint?
3 times log sub x plus 2 equals 7?
No. Yes, Rajay.
Log base 3 of 7 equals x plus 2.
Exactly. Okay. So before we go on to the next one, look at the correspondence. We have a to the x equals b log to the base a of b equals x. And so the exponent corresponds to what the value of the log is, and the bases correspond to each other. And so think of it as undoing. When we have a to the x, it gives us the number b. And then when we have log to the base a of b, gives us x. And so it's a way to undo this if we're looking for x. If we have a and b, then we can put them in this half of the equation and it'll directly evaluate into x. So it's useful in defining a function this way. Okay, how about this one now? What about 10 to the e equals x? Heather?
I know what it is, but I'm not sure how to realize it.
Okay.
So it's log with the 10 in the subscript and then x and then equals e.
Great. Okay. So you probably wrote it like that, right?
Yeah.
Okay. So we'll say log base 10 of x.
Okay.
Okay. So the log base 10 of x equals e. Okay. And so we have this last one here. E to the fourth equals x plus 1 squared. Now put that into logarithmic form. Don't bother simplifying it. There is a simplification that once you rearrange it that we'll get to, but if you know that, don't worry about it, we'll get to it.
Are you telling us
Just make this kind of transformation of it. Okay, so just rearrange its components. So instead of having all these superscripts around, put a subscript after a log and fill in the blanks. Cassandra, did you get that one?
I don't know if I, but I did log base b to the x plus 1 squared equals 4.
Right. Yes. So it was log base e of x plus 1 squared equals 4. Now, one of the things that you have to be cognizant of with the log expression is that functions in your order of operations go first. And so if I were to write something like this, where I would have the log of x plus 1 is different than the log of x plus 1. The order of operations say that you would take the logarithm of x before you'd add the 1, and here you would add the 1 to the x before you do the log. So keep in mind your parentheses. When in doubt, put a parentheses there. Okay. So I mentioned that there's some notation shortcuts, and I actually wrote one on the board here that will become pretty important to us. When we talk about the base 10 log, we can just write that as what we call the common log. Log of x, we imply that that's the base 10 or we're using the base 10. Now, the other one that you'll see on your calculator, you probably on your calculator have just where it says log. That's the base 10 log. The other one is the log base e of x. We write it as ln, and that means the natural log. So if we write it without a subscript, it's base 10. If we write ln, that's still logarithm, still has the same meaning, except that it suggests that we're using a base e. Now you would think that in the metric world that the common log, since that's base 10, would be used there as well. And it depends on where in the world you are what log of x means. And it happens that in the use a pencil mathematical world, it's almost universal log and ln for the natural log. In computers, though, you have to be really careful, and you have to be very clear about what log you're meaning. So the three languages that are most often used for computation, MATLAB, Mathematica, and Python, the log of x is the natural log. Okay, so you always have to test that first. So the deal is you put in a value for x and see what it is, and we'll know some easy rules of thumb that will tell us. So if you take the log of 10, you should get a 1 if it's the common log. If the log of 10 is something other than 10, or other than 1, then you have a natural log. Okay, so just be careful on that if you ever get into computer programs. This will be posted after class too. And I don't mind that you do that, okay? But it's probably not necessary. Okay, so let's talk a little bit more about domain and range before we get to some of the other properties. You know, remember what the exponential functions look like. They start off really close to the origin as x goes to negative infinity, and then it gets really, really big without bound as x goes to infinity. Since we're looking at inverses, okay, what we want, or let's first consider this. The a to the x, the domain is all real numbers. You can put in any number, any real number as an exponent, and you get something. And what you get is always a positive number. Okay, so the f at x always ends up to be more than 0. Right? So if you take 10 to the minus 100th, you're ending up with a very small number, but it's still positive and it's still non-zero. So with the inverse now, we're going to expect that it looks like this. Remember when we were plotting inverses, it would be symmetric about that line that goes 45 degrees through the origin. And then also think about the domain and range. The domain of the inverse of a function is the range of its original function. So the domain of the log has to be all real numbers. Now I made a little notation kind of error here. Here I'm putting a, and here I'm using the log of x, and this probably should read log, let's see if I have my little stylus. I'll do it with my finger. This should really be the log base a of x. How's that? So then the range is you can get all real numbers. So you can get negatives out of logs, but you have to give it a non-zero number. So the log of 0 in any base is undefined, and that's undefined as division by 0 or you know, the square root of -1. It's just not a real number. Now, when you deal with complex numbers, that question or that answer changes, but we only deal with real numbers, and so we look at the domain and range like that. So it's important to remember. Okay, so let's look at some of the properties of logarithms. And at first, you know, we'll remember that if our function is a to the x, the inverse of the function is the log base a of x. And so if we take the inverse of the function, we should get the original variable back, right? So if I take f inverse of f at x, okay, I'll stick the f at x in there, so I have the inverse of a to the x. I'll get log base a of x to the x power. Okay, so just by definitions of inverses, we know that that's going to equal x. So this is going to lead to one of our first properties here. If we do it the other way around, if we take f of x inverse of x, that's like taking f of log a of x, and that will look even more strange, where we have log a of x in the exponent. That just equals x as well. Okay, so here are a couple examples of the composite of the function and its inverse. Okay, so let's look at a to the 0 power we know is 1 when a is not 0. So log base a of 1 equals 0. So whenever we take the logarithm of any base of 1, we get 0. You can try that on your calculator if you want, but it's exactly 0. And the other one that we're really familiar with is that a to the first just equals a, right? And so if we put that into the other form, we get log base a of a equals 1. Now this is going to be a very important thing to know. So whenever you take the logarithm of a number, the logarithm using the base that's equal to the number, you get 1. All right. So those 4 things you should know. The hardest one to visualize often is the second one here. When you see logarithms and exponents, people go, people tend to have a little bit of a mind block or a mindset against that one just because it looks odd. But try and think about what it's doing. A to the exponent is the function. The logarithm of x is going to be the inverse, and so the function and its inverse, if you do them as a composite function, you get the original variable out, and that's what you have here. Okay, so let's look at some examples of these where this would come in handy. So the first thing that we want to do is when we see numbers that are some power of the base, what we want to do is we want to write it as log base 5 of 5 squared. So what does this equal then? Okay, think about the first thing that I wrote was that the log base a of a to the x equals x. Okay, so here we have the log base 5 of 5 squared. That makes that 2. Okay? It's just plain old 2. Now, this also works with negative exponents. So if you have 1 over 27, recognize that 27 is 3 cubed, but it's 1 over 3 cubed, so it's actually 3 to the negative third. And so if we rewrite this expression as log base 3 of 3 to the negative 3, what does that equal then? Negative 3. Okay, so here's an example where 1/27th is still a positive, non-zero number. Okay, so we're okay from a domain standpoint. We get a negative out of this, and that's what we said, that the range of the logarithm is going to be all real numbers. So here's an example where we actually get a negative number out of it. Okay, and so if you look at radicals as exponents, this one falls out the same way as the first one, where square root of 6 is just 6 to the 1/2 power. And so the answer here is 1/2, right?
So I have a question.
Yeah.
So like written in the way that you have it, log base a of a to the x equals x, x is still considered like the exponent, right?
Mm-hmm.
It's just
Yeah.
a more complicated version of writing it.
Think about a logarithm giving you the exponent that you apply to the base to get to this number. Okay? Ranjay.
This is completely unrelated, form of calculator stuff. How do you take like a square root, like instead of square root, like 20?
Take the reciprocal of the 20. So if you want to take the 20th root of 5, it's 5 to the 1 over 20,
Okay.
right?
Okay.
And I won't even regress you back to math 13. How's that? That's big of me, right? Okay. All right. No, that's all right. It's okay. So the log of 100. Here we have the common log. So we think, oh, okay. So this is base 10. 100 is a power of 10. So we write that as log of 10 squared, and that is 2, just by the same reasoning as we had in the very first one. Okay, so here's one for you to try. Actually, 2 for you to try. Okay, Sarah, did you get this?
I got the second one.
The second one. Okay, what's the second one then?
Equals
3, good. Anybody get the first one? Sean? It's 2, no?
No?
No, because the log of 100 is 2. This is the log of 100. Okay? Negative 2. Okay, it's 10 to the negative 2 makes 0.01. And we got 2 cubed is the same as 8, so that makes that 3. Okay. So this directly goes to how do you do those questions with the e's in there. At least it should help. Oftentimes we want to make or it's easy to make a expression like this. Okay, so we have just an arbitrary number here. But scientifically, what's more common is to have e to the kt, where k is some constant. Now, converting these back and forth is not nearly as difficult as it may seem. Okay, so if we want to do this, the coefficient is unchanged in this. Because, you know, when t is 0, that constant a is the initial value, right? And so the initial value, whether it's 2 to the t or e to the kt, are both 1, and so the initial value stays the same. So then we look at e to the kt slightly differently. Okay, remember when we have exponents multiplied, that's taking one power to the next power. So e to the kt is the same thing as e to the k to the tth power. Is that? Anyway, you know what I'm saying, right? It's this. Okay, so then we know that 2 equals k, e to the k. And so let's solve for this. The way we solve this now is that we'll take the natural log of both sides. And remember, the natural log of e to the k is just k, so the log of 2 equals k. And you do that on your calculator. The natural log of 2 is 0.6931. So now we just make a substitution, and there's our equation. So this function and this function are exactly the same. Now, we've already established how we do this, right? So if you have 2 points, how can you make this? Remember, we just by substituting what y and what t equals, you can figure out what a and b equals. And if you want it then in this form, what you do is you first figure out this form of the equation, and then you get down to this point where whatever's inside that parentheses is e to the k. And so you take the natural log of it, and then you get that k factor. Okay, so I'll let you noodle with that until Wednesday, and then we'll do some of these in class explicitly. That was on WebWork, okay? But that should be plenty to get you going on that. Okay, so if we're going to do it the other way around, it's just as easy. And so the coefficient stays the same. E to the minus 2 equals b, in this case, this b. And so we just take e to the minus 2, and we get 0.1353. And so then the function is translated into that. This is a less common direction to go. Usually what you want to do is put everything in terms of e to the sum expression. But if you need to go the other way, or if you want to go the other way, you can do it like this. Okay, so why don't you just try this one? I think most of you have your calculators. If you don't worry about it. But actually, knowing the properties of logs, all you need is the last slide to do this one.
you actually go to the last slide?
Hmm?
Can you actually go to the last slide?
Mm-hmm. And you don't need your calculator at all, knowing the properties of exponents and logs and reciprocals, right? You know what I'm talking about, Sean? You smiled, yeah. Okay, we'll go back to the original problem now. Okay, so remember that e to the kt is the same thing as e to the k to the tth power. And so when you solve this, the coefficient is the same, and we have 1/2 equals e to the k. The log of 1/2 equals k. Now notice that numerically is exactly the same. It's just negative, right? And that's no coincidence. The log of 2 is minus the log of 1/2. So reciprocals, there's a little thing in here, we'll get to the formal rule on that, but when you take the reciprocal, when you take the log of a reciprocal, you get the negative version of the original number. And so what's, yes?
I'm not really sure what happens between the third step and the fourth step.
This one here
Yeah.
to this? Okay, so I know I can calculate this on my calculator, right? And then here I have the natural log of e to the k, which is going to simply be k then, right? So I can calculate k directly just by taking the log of 1/2. All right, and then I get that. So then my function then is f at x equals 100 e to the minus 0.6931 t. Yes, Sean?
Does it become k by you taking the k to the front, and then ln e being 1?
Yeah, that's one way to do it, but here since I haven't established that yet, I'm using the property that when I take the log of e to the k, that's simply k. I'm using, you'll see where we're going with this, but and we'll do it that way because that way the base of the log doesn't have to be the same as the base of that expression, which is perfectly valid, and that's probably the way you'll end up thinking about it. But here, since I've only introduced the inverse, or the function and its inverse, it falls out that way. Okay, so let's move on. Okay, so more properties here. Now we're going to get into a few more, take them probably a little faster. So here I have two expressions, a to the b equals x and a to the c equals y, and I'm going to write them as the log of ax equals b and the log of a of y equals c. So I'm just making some definitions here. So I have the same base, but I'm taking a to the b in one of them, a to the c in the next one, and so when I take the log of x and the log of y, I get b and c back. Okay, so let's start combining these things and see if we can come up with a property here. If we multiply a to the b times a to the c, we add exponents there, right? So that's a to the b plus c, and since we've multiplied those two together, that equals xy. Okay, so no trickery here. This is just taking a to the b times a to the c, add those exponents, and since I've taken x times y, I just write it that way. Okay, so if I write this as a log now, I get the log of a of xy equals b plus c. Okay, so all I've done is rewrite it into logarithmic form. But notice now, I have b here as the log base a of x, and I have c here as the log base a of y. And so when I put that all together, I get this really marvelous identity. And so this turns out to be one of the most important rules in logarithms.